So for number 12, I left 11 up here so that we could look at the comparison. Notice that the denominator here for number 12, we have s squared plus 2s. The difference between 11 and 12 is that on 12, we can factor this denominator into two linear factors. And so we can take that fraction off to the side and do some partial fraction decomposition to break this up into the sum of two fractions. And we need to solve for the coefficients or the numerators. If I multiply through by s times s plus 2, that cancels out all of my fractions, and it leaves me with 1 equals a times s plus 2 plus b times s. And if I combine my like terms on the right side, I'll have as plus 2a plus bs, and then the as and the bs are like terms. Factoring out the s gives me a plus b times s, and then I have 2a. That's equal to 1. I'm going to put an s term there. It's going to give me a 0s plus 1 is equal to a plus b times s plus 2a. So I know that my s coefficients have to match up for this to be true, and that tells me that 0 is equal to a plus b. And then my constant terms also have to match up, and that gives me 1 is equal to 2a. So from here, we know that a is 1/2, and we know that a and b are opposites because they add to 0, so that tells me that b is negative 1/2. So a is 1/2, b is negative 1/2, and I'm going to go back to my inverse Laplace transform and rewrite this in as a sum of fractions. That gives me 1/2 times 1 over s minus 1/2 times 1 over s minus 2. And the transforms that we'll use is the transform of 1 is 1 over s. The transform of e to the at is 1 over s minus a. On this, oh, I forgot. Yeah, no, I did not forget. On this first one, I have the inverse transform of 1 over s. That's going to give me a 1. That 1/2 is a constant, it just carries. And then that negative 1/2 just carries along. And the inverse Laplace transform of 1 over s minus 2, here my a is 2. A is 2. I get e to the 2t. So you might multiply out that 1/2, or maybe not. However you want to write that. And that's number 12.